Now, we will learn how to compute vertical stress increase at a point within the soil mass due to some loads at the ground level. These are the assumptions we make for developing expressions for computing the vertical stress increase at a point. We treat soil as a linear elastic continuum, with a constant Young's modulus and Poisson's ratio. Hence, we can apply the principle of superposition. We compute the overburden pressure as the product of unit weight and layer thickness for the entire soil mass above the point of interest. When there is a surcharge Q of large lateral extent, it just increases the vertical stress at all points within the soil mass by Q. However, if the surcharge Q is spread over a limited area, the increase in vertical stress at a point will be less than Q and will depend on a few factors. The vertical stress at a point is the overburden pressure plus the increased delta sigma V caused by the surface load. In this chapter, let's just focus on the increased delta sigma V and look for ways of determining that. The delta sigma V depends on the shape of the loaded area, magnitude of the applied pressure, and the point of interest. First, let's discuss the vertical stress increase due to a point load Q at the ground level. Here, we have two expressions, from Busnisk and Westergaard. Here, we ask you to sketch the variation of the delta sigma V along the two horizontal lines and the two vertical lines, based on your gut feeling. Let's compare the stress increases computed by Busnisk and Westergaard expressions. We can see that generally, Busnisk gives higher values than Westergaard. Thus, Busnisk is more conservative and hence popular. Here is the expression for line load, obtained by integrating Busnisk equation for point load. This is for computing vertical stresses due to a uniform strip load. The angles are in radians. Now, we want to find the delta sigma V at depth set under the corner of a uniform rectangular load. We simply develop an expression for the stress increase caused by the infinitesimal element shown in blue, using Busnisk equation for point load, and integrate over the entire area. We end up with a long expression for the influence factor I in terms of M and N, which are given by B on Z and L on Z. Note that M and N are interchangeable. We can develop an expression using Westergaard equation for point load too. Here, Poisson's ratio comes into the picture. Here, we graphically present the influence factor I as a function of M and N. The MN charts using Buznisk and Westergaard equations are shown here for comparison. You can see that Buznisk values are larger. It is good to be conservative in engineering. So, when there are two sets of values for the applied stresses, we would use the higher ones. This is a straightforward exercise to apply the MN chart to find the stresses at different locations beneath the loaded area. This is an approximate method to carry out back-of-the-envelope calculations to determine delta sigma V under the center of a uniform rectangular load. We assume that the load spreads with a slope of 2 vertical to 1 horizontal, on both sides of the rectangle. With the base area increasing with depth, but still carrying the same load, the delta sigma V decays fast with depth. In the first expression, when L tends to infinity, we get the second expression for strip loads. Let's just be concerned about the vertical stress increase at a point on a transverse vertical plane through the center of square and strip uniform loads of width B. Using the MN chart, it is possible to find the stress increase at any point on this plane. When a uniform pressure of Q is applied at the ground level, we can locate the points where the stress increase is, say 0.6 Q. Connect the points and draw the contour as an isobar for 0.6 Q. Here, we have drawn the isobars for 0.1 to 0.9 Q. The left half is for square and the right half is for strip. This chart with isobars is handy for finding the stress increase at any point on the transverse plane of symmetry. These are isobars for a circular load. Here we ask you to try the 3 different methods to compute the stress increase delta sigma V for a rectangular footing and then repeat this for a strip. This is after Oosterberg from 1957. For finding vertical stresses along the vertical centerline of a symmetrical embankment. In fact, it is possible to find the vertical stress increase at any point under the embankment, not just along the centerline. Here is the closed-form solution for the vertical stress increase at a point on the vertical centerline of an embankment. This is the equation to find the stress increase along the vertical centerline of a uniform circular load. For points that are outside the centerline, use this chart. Note that for r on A larger than 1, the point is outside the loaded area and hence the stress increase is quite small. So far, we dealt with point loads, line loads, and uniform rectangular and circular loads. When there is a uniformly loaded but irregular area, we have to go for Newmark's chart. Let's do a simple exercise before looking at Newmark's chart. Here, we ask you to compute the required radius of the circle carrying pressure Q, in terms of depth Z, such that the vertical stress increase at depth Z is say 0.1 Q. Repeat this for 0.2 Q, 0.3 Q and go on up to 0.9 Q. This is the basis of Newmark's chart. For example, we will see that we have to apply Q over a radius of 0.2698 Z to see vertical stress increase of 0.1 Q at depth Z. Now we use the 9 different values we computed for the radius in terms of Z and draw the circles. The length Z is shown to scale at the top. The pi is divided into 12 by 10, which is 120 blocks. A uniform pressure Q applied in any one of the blocks will impose 1 on 120 Q at a point located at depth Z below the center. It is important you understand this point, which is the basis of using Newmark's chart. Newmark chart can have any number of blocks. The one shown here has 120 blocks and the depth scale is shown at the top. Measure the scale in millimeters. Redraw the plan area of the uniform load such that the depth of interest is equal to this scale. Overlay the redrawn plan area on top of the Newmark's chart such that the point of interest X coincides with the center. Count the number of blocks covered, including fractions. I in this chart is 1 on 120. In this section, we will also have a brief discussion on computing elastic settlements beneath flexible footings. We are looking at 3 cases, and then combine them all to arrive at a general solution. The equation at the top is the standard elastic solution for settlement at a point on a uniformly loaded flexible footing. The first case is a surface footing on an elastic half space. We can use Schleicher 1926 solution. The I here is for a corner. Like before, using principle of superposition, we can find the settlement of any point on the footing. Compute the settlement induced by each of the 4 blocks and add them up. We are using the principle of superposition. In case 2, we allow for a stiff stratum to be present at depth h still, it is for a surface footing. Using the m' and n', first find the 3a values. Then find the 2f values. From these, you can find the I corner. Now we go a step further and allow for foundation to be at a depth and determine the embedment factor suggested by Fox is 1948. Multiply the settlement by this factor.